So states of matter, chapter 3.1 and 3.3. All right. So for the entire topic of states of matter and phase changes, there's one governing theory that helps us understand what's going on when something changes from one state to another, or what's going on for the particles in each state of matter. And that's the kinetic theory of matter. Kinetic theory of matter. From your reading, you should know what the kinetic theory of matter is. Who remembers from Friday? Or who wrote it down and can just look it up real quick? Yeah, go ahead, Taylor. All right. So when that's specifically kinetic energy. So that's a huge part of the kinetic theory of matter. So we'll get to that in a second. Maddie, what do you have? All right. So when we're talking about the kinetic theory of matter, the basic idea behind it is that all particles of matter are in constant motion. So all particles of matter are in constant motion. In constant motion. The more the particles move, the more energy they have. And that energy is called kinetic energy. The more particles move, the more energy they have. And that energy is kinetic energy. Okay. The other piece to the kinetic theory of matter that we're going to make sure we've got in here is that at the same energy, things that are smaller or smaller particles move faster than larger ones. For the same amount of energy, smaller particles move faster than larger ones. So if you or I are looking at an object and we have, let's say we're looking at two objects rather, how can we tell which object would have more energy? If we're looking at two objects, how can we tell which one has more energy? Yeah. Okay, not necessarily by size. That would help us with determining for size of particles how fast they're moving. Yeah. Say again? State of matter would definitely be one thing that would help us out. But what if they're both solids? If we have two solids and we're looking at them both, how could we tell which one has more energy? Sana. Okay, heavier is a good thought, but that's not going to help us. Caleb, do you have an answer? Okay. MK, did you have an answer? Okay. So we can figure out which one has more energy by figuring out which one's warmer. Kinetic energy is interpreted by us for particles as how hot an object is. So when we're talking kinetic energy here, what we're really saying is how warm is the object. So temperature is a measurement of an object's kinetic energy. Temperature is a measure of an object's kinetic energy. All right. So this is the theory that helps us understand what's going to be going on for different objects. What we want to do now is we want to take a look and see how that actually applies to different objects, starting with solids. All right. What properties make something a solid? What properties make something a solid? Someone who did the reading Friday. Say again? What about it? Yes. So definite volume. And what's the other one? Definite shape. All right. So solids have definite volume and definite shape. That means that just by sitting here, for example, this stapler, it's got a specific shape. It's got a specific amount of space it takes up. That's not changing. It's got to hold this much space. Okay. When we start talking about what's going on at a smaller level with the particles of the stapler, we can start to see how the kinetic theory of matter applies. First of all, does this stapler appear to be in motion right now? No. What we need to understand is that the particles that make up the stapler are in constant motion. So just like you guys, after you've had too much sugar and you're probably vibrating and jittering in your seats, the particles of a stapler or of any object always have enough energy that they're vibrating in place. So the individual particles vibrate in place. The hotter they are, the more they vibrate. The colder they are, the less they vibrate. Okay, so all particles are in constant motion. How are they moving for a solid? They're vibrating. The more they move, the more energy they have. The hotter the object is, the more they vibrate. For the same amount of energy as smaller particles, that was pretty self-explanatory, and we talked temperature. All right, moving down the list. Liquids. What properties make something a liquid? Definite volume and anything else? Good. So definite volume, but they take on the shape of their container. Of their container. All right, so if solids were you guys on too much sugar, if we then give you a Mountain Dew to top of that off, what are you likely to start doing? You'll start probably getting up out of your seats, kind of meandering around. You'll probably forget that you're supposed to be sitting, and I mean, some of us will probably be jittering, maybe bouncing. Liquids kind of behave the same way. They start sliding past each other. They don't have to stay in one location. They can rearrange with relation to each other. So particles slide past each other. All right, next up, gases. What makes something a gas? Go ahead, MK. Yes, so it always expands to fill its container. And Maddie? Okay, no definite shape or volume, but it will expand to fill its container. No definite shape or volume. Will expand to fill its container. All right, so solid was you guys on a little too much sugar. Liquids was you guys on a Mountain Dew and too much sugar, sliding past each other. Gases, now we're going to top you off with a shot of espresso. And how would you likely be behaving? And a few of you will be bouncing off the walls, quite literally. So gases, the individual particles, are in utter chaos. They're flying by randomly. They have no attractive forces between each other. They're just going wherever they please. So rapid, random motion between particles. All right. Questions on the differences between any of those? Okay. Then the next thing we're going to talk about real quick here are what we call phase changes. So this is a little bit more of 3.3. Phase changes. So we haven't read this section yet. A phase change is the same thing as saying changing state of matter. And your book uses a diagram really to help explain this. I think it's a really good diagram to use. So we start out with gas, and over here we're going to have solids. And over here we're going to have liquids. Okay, so if we have a substance, I mean something like an ice cube, and it goes from a solid to a liquid, what is that process called? What's it called when something turns from a solid to a liquid? A little louder. Melting. Okay. How about when it goes from a liquid to a gas? Evaporating. Sano, is that what you were going to say? All right, thank you. All right. How about from a solid to a gas? Say it louder. Sublimation. So in each of these three types of phase changes, we're going from something that we could consider a lower state of matter to a higher state of matter. We can say they're going from lower to higher because that's how the energy is organized. Solids always have the least energy, gases always have the most energy. Sublimation. S-U-B-L-I-M-A-T-I-O-N. So each of these three phases are what we call endothermic. An endothermic phase change, or an endothermic reaction, is any reaction that absorbs energy. Any reaction that absorbs energy. So in order for ice to melt into water, it needs to absorb energy from its surroundings, meaning that its temperature is going to go up. Okay? In order for liquid to evaporate into a gas, it needs to absorb energy to evaporate. Okay? Just as we've got these steps to go up into a higher state of matter, we can also fall to a lower state of matter. If you've got a different color, I recommend drawing this next part in a different color. What's it called when a gas turns into a liquid? Say again. Condensation. Okay. How about when a liquid turns into a solid? Freezing. And here's the tricky one, a gas turning into a solid. Anybody got a guess? This is the hard one. Yeah. It is deposition. Nice. All right, deposition. So if we're going in terms of how I wrote it, the blue pen, condensation, freezing, and deposition all go from a high state of matter to a low state, meaning they all lose energy. So an exothermic reaction, is any reaction or any change that gives off energy. Gives off energy. Okay? So, question for you here. So yesterday was unreasonably hot, right? Anybody go outside yesterday? Okay, so I am willing to bet that if you went outside yesterday, at some point you started sweating because it was like 94. Okay? Sweat is something that our body does in order to cool our bodies down. We all know that. But which phase change takes place when you sweat? Which phase change takes place when you sweat? Yeah. That's raining. Evaporation. Because when you've got sweat, you've got water on your body. And as it evaporates, it turns into a gas and suddenly it's gone. Now, why does that help our bodies lower their temperature? Well, in order to go from a liquid to a gas, do you need to absorb or give off energy? Well, since evaporation is an endothermic reaction, it absorbs energy. So when sweat goes from a liquid to a gas and evaporates, it absorbs energy. Where does it absorb that energy from? What would be readily present? Your bodies. So when liquid sweat goes from liquid to gas and evaporates, it absorbs energy from your body. When it absorbs energy from your body's temperature cools down. So by sweating, we can see that we've got an endothermic reaction going from liquid to gas. The last thing that I want to write down here is that whenever we're talking about hot objects and cold objects, hot objects always give energy to cold ones. Hot objects always give energy to cold ones. Okay? So you can't transfer cold. That doesn't happen. It can't exist because cold isn't a thing. It's the absence of energy. Okay? So if you're holding an ice cube, you're not absorbing the cold from the ice cube. The ice cube is absorbing the heat from your hand. Does that make sense? The heat is energy, and energy has to flow from hot to cold. Also, I want to point out, there's no such thing as cold energy. That's not a thing. Energy is energy. More of it means you're hot, less of it means you're cold. Caleb. If they're the same temperature, no. But your hand being the same temperature as ice cream means you should probably be looking at going to the hospital because that's not safe. All right. Unless there are questions about endothermic or exothermic reactions, unless there are questions about this phase change triangle, then what we're going to do for the last portion of class is there is a assignment on the